module parameters. Remember, we're in a module that's parameterized by the type of keys, the comparison function, and the values. And the reason that those get written there is that module parameters are really syntactic sugar for parameterizing each component of the module by those values. So sometimes internally that's represented as ins is parameterized by these things, and so those get printed out sometimes. So you can just kind of gloss your eyes over and ignore that bit. The node and the kv are exactly the arguments to ins in this case, right? Those are the arguments that we, what do we call them? It's the t and the kv that we determined when we applied HBH node to those arguments. Okay, so just like we specialized to empty in the previous case, we specialized to node in this case. Good? Okay, so what's this vertical bar thing? This vertical bar thing comes from width. So if you look at the definition of width, definition of ins, we scroll up to that. Ins is defined by saying width compare kk prime. Okay? And what width is really doing, the way to think about it is, it's adding another column to your pattern match. It's adding another column to your function and calling that on the value compare kk prime. So you want to think of this as I'm applying ins to the argument compare kk prime that I'm then going to do further case analysis on. And the bar is Agda's notation for separating the actual arguments to the function from the ones that are determined by the width. Okay? So what's going on here is that you can think of it as I've called ins with this extra column of my pattern match for compare kk prime. And now the argument that I called ins in the extra column on is that. And operationally what happens is ins waits for compare kk prime to reduce to one of equal, less, and greater, and then computes. So what we need to do in our, so what we have down in the goal is a case of ins where this is stuck, because we don't know how the comparison shakes out, right? We don't know whether k is less than k prime or k is greater than k prime. And so ins is also stuck. We don't know whether how ins computes yet. Okay. So what do we do when we have something that's stuck and we want to prove something about it? Pattern match. So what we'd like to do is we'd like to pattern match on compare k prime. Okay? How do we pattern match on compare k prime? Using another width. So when you have a width in your code, you're going to need a width in your proof. So we can do a width compare kk prime, okay, here. And then on the next line, we'll put dot, 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 and then a bar to say, here's the argument for the width. And then let's call this, I don't know, C for, or no, we already use C. Let's call it comp for, or res or something for compare result. OK? So now, really subtle thing is going to happen. So let's look at the goal that we have here. What's different about this and the goal before we did the width? What changed? Yeah.
The bar compare substitute to bar red.
So we replaced this with res, okay, where res is the name for the comparison result. So this is magic, right? This is a feature of Agda that we have not talked about yet, which is that when you do a width, Agda takes the context and the goal and replaces all occurrences of the term that you're doing the width on, in this case compare kk prime, with the variable or patterns that you conclude in the case that you use in the cases of the pattern match. So you're ripping out compare kk prime and saying, let's replace that with something else. Okay, so this is like you would use a rewrite in cock or something like that to accomplish this sort of thing. So you're ripping out something and replacing it with something else based on the pattern match. Yeah?
So sometimes in cock rewrites fail because the cock's best guess results in an ill-type term.
OK.
Does that ever happen when you try to do something like this in Agda?
No. So like you can always with on a term. So it's doing this up to definitional equality. So anything definitionally equivalent to the term that you with on gets ripped out. OK? So you could always do this by hand by writing a helper function that kind of did this pulling out. But that gets annoying fast. And so the magic of with is that it pulls out that thing for you and rewrites the goal so that now it mentions res instead of compare kk prime. OK? And yeah?
So if you have some other proof that gets typed as the particular thing that you're trying to do with on.
It'll get pulled out there too.
Okay.
Yeah. So yeah. So like if you're going to have a construct that just says pull stuff out, then the only choice is to say pull all occurrences of it out. If you want to only pull out some specific occurrences, then you have to write a helper function yourself. OK. So now what we've got is this state where bar is res. And now what we can do is we can pattern match on res. So we can say, let's look at what the comparison returned. So if we case analyze res, then we get cases for less, equal, and greater. And if we look at the equal case, then we'll see that now, hey, this whole ins stuff went away. Ins is gone. What we have left is showing that a node has a black height. And why is that? It's because when the comparison computes to equal, inserting computes to node. OK? So now we've unstuck our reduction, and we can go on with the proof. So let's fill in the equal case. I don't know how to do it, but let's just refine. OK, so we need to show that a node has a black height. Then we need to show what? That L has some black height. Hey, fortunately, we have a proof that L has some black height. That's HL. Now we need to show something. Hey, we have that. That's CH. And then over there, it's probably going to be HR. OK? So when we do the proof that ins has a black height, it's pretty much the same structure as the code for ins. We've taken, right, so like in the equal case, the code says just put the new key value at the root of the node and keep everything else unchanged. Here the proof says make a node with exactly the same arguments that were coming in. OK? Good? All right. So for equal, for less, OK. So what do we need to do here? Here we need to do something about balance. So we're going to need a lemma about balance in order to do this case, because we need to conclude that a call to balance has a black height. And we can state the lemma for balance as essentially the same as the type of the constructor for HBH node. OK? So if we go write that, we're going to have a lemma that says that balance has a black height. OK. That's going to say, given any, so it's got actually more arguments than that. So it's got a left subtree, a color, a key value, a right subtree, and an m. This really looks a lot like the one for node. Right? So OK, so for all of those things, if the left subtree has black height n and the right subtree has black height n, and sorry, in between those two, let's put a color height cmn. So really this is, OK, yeah, cmn, cnm, sorry, blah, 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 blah. Under that condition, then the call to balance has black height m. OK. And you can see now they're both on the screen. Really what we did here was to take the type of HBH node and write out exactly the same thing, except instead of making node LCKVR, it's balance LCKVR. Okay? So the lemma is that balance does the same thing as node in terms of coming up with the black height. Okay? Good? Okay, so with this lemma in hand, let's do the case for less. So in the case for less, what we're going to do, so the reasoning here is as follows. L has black height n, R has black height n. Okay? So by induction, we want to show that balance inserting into left R has black height m. By induction, inserting into the left is going to preserve the black height, because that's the thing we're proving about insert. Then by the lemma for balance, we're going to get the result. Okay? So the way we write that proof is we call the lemma for balance. So we'll call balance BH on, let's see, 1, 2, 3 explicit arguments. Okay. And then in the first one, what we're going to do is, so this underscore blah, 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 underscore blah, 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 is saying that right now Agda's kind of confused about what we're supposed to do, because there might be different ways we could supply these arguments that would work. Okay? So since Agda is doing this thing by figuring out these goals by unification, sometimes it can't actually figure out exactly what we're supposed to do. But fortunately, we know what we're supposed to do, which is to make the recursive call ins-bh on kv, or sorry, on underscore and hl, or kv and hl, k comma v and hl. K comma v. Space before the comma. Okay. Okay. So what we said here was by induction, and maybe you can put that on the great. Okay. So what we said here was by induction, right? We insert into the left, and that preserves the black height. We represent that by a recursive call in our proof to ins-bh. And then over on in number 2, we can fill in HR. And in number 1, we can fill in CH, since, spoilers, we just did that. Okay. But now if you look at the goal there, well, that's good. Okay. So you can look at that if you want, like, if you want to like work through the details of that after. But the basic idea is we formalize this argument that says, by induction, we insert into the left, that preserves the black height. HR says that the right has the same black height, then we just put them the two together by call the inductive hypothesis, call balance. Okay? So the thing to observe there is just that inductive hypotheses, when you would think of the proof on paper, turn into recursive calls when you're writing the function. Okay? And note that this has, again, exactly the same structure as the call to, as the code, right? The code for balance, or the code for insert says recursively insert into the left, and then call balance. The proof for insert says apply the inductive hypothesis for insert, and then apply the lemma for balance. Okay, we're really tracking the structure of the code. Okay, and if we do the right case, it's going to be exactly symmetric. So it'll just be, we can just write it, balance hyphen bh of hl, ch, and then ins bh on hr, or kv comma hr. And refine, and we're good. Okay. Any questions about that proof? The big new thing there is this with, right? So the fact that with rips out the subterm and lets you make progress. Yeah?
Are there basically simple rules of thumb that might help decide when to use with in writing these?
Well, so basically, the way that we decided to use with was we looked at the goal. We saw that the goal was stuck on compare kk prime, right? The goal.
Not in the proof, but in the.
Oh, in the code? So like basically you should use with whenever you would use a subsidiary case analysis in ML. So there's no case in Agda, right? So whenever you're saying, I get these arguments and then I want to pattern match something else, use with. Okay? Yeah. Okay, good. All right. Let's do, sorry, where am I? Okay, let's first do insert BH just to finish this off. So we can chain these all together to prove that for any number in any tree T and any KV, which is a key value, and tree is misspelled there. Good. Okay. If T has black height n, then insert into T has of KV has black height, well, something, right? So because insert calls black in root and black in root produces an existential, let's just say there exists some m such that the insert has a black height, right? Because we want to verify the property that the tree has a black height. So we need a sigma out front. So sigma before that. Yeah, sigma lambda m, oops, goes to that. Okay. And remember, there's this slight weirdness with sigmas, which is sigma is just a defined type, and the argument to it is a function, which is why you write sigma applied to lambda m goes to that. Okay. So now we can prove that spec. So how do we prove that insert has a black height? Let's go look at the code for insert for a second. So the code for insert says that when we do an insert, what we do is we do an ins recursively, and then we blacken the root at the end of the day. So the proof for insert is going to be, hey, we call our lemma about blacken root black height on calling our lemma about ins. So here we need to show that ins has some black height, and that's what ins bh on underscore, and so underscore is for the KV argument that we made explicit for silly reasons, and then h will do. Okay, so if we do that, good. Okay, so modulo the lemma about balance, there is a proof that insert preserves the black height. Okay, and you can see that we're again tracking exactly the structure of the code. Insert calls blacken root and ins. Insert bh calls blacken root bh and ins bh. Okay, so let's see. I started like when?
20 minutes.
Yeah, so wait, if we started at
45.
Yeah, we started at like 45, right? So we've got about 20 minutes. Okay. All right. So I think, given that we have about 20 minutes, let's skip balance. And so I'm going to not do this balance lemma. There are some complications in doing balance. This is all written out in the notes. You can take a look at it. But we're just, yeah, like let's just skip that because I want to go on to the next thing. So what we've done here is to do, let's see, we started off talking about extrinsic versus intrinsic verification. Okay? This right here is a good example of extrinsic verification. We took the code that's just a simply typed program. We wrote a proof about it. Now let's do the same thing with intrinsic verification. Okay? So if you scroll down in the file, you have another copy of the code. And the idea with intrinsic verification is that instead of writing the code and then doing the proof, we're just going to do the two kind of on top of each other. So the way we do that is instead of defining trees and then defining when does a tree have a black height, we're just going to define a type of trees that tell you their black height. Okay? So we can make tree an inductive family. So we'll change the type of tree from set to nat arrow set. And then we'll take HBH empty and HBH node, right, the constructors that tell you when trees have black heights, and turn their types into the types of the tree constructors. So empty will be a tree of black height 1. Okay. And node for any n and m of type nat will be, say, if you give me a tree of black height n and a color and a tree of black height n, then the result is a tree of black height m. Okay, so what's wrong with that?
We need the m to be constrained.
Yeah, so we need to constrain the m to be, well, successor of n if it's red, if it's black, or n if it's red. Okay? How can we do that? We can take color and turn it into color height. What does color tell you? A color really tells you the relation between the height of the subtrees and the height of the result. So color will be a relation on nat. You can just, yeah, OK, that's fine. For now, let's just say that that's equivalent to if you had written nat arrow set. Let's just do the other version. I don't want to get into this now. Yeah. Color colon nat arrow set. And red will be for any n, right? So implicitly for any n, color nn. So you need to put a pi there. Put a pi in the type of red. Yeah. So implicit pi n colon nat. Good. Arrow color nn. OK. And black will be for any n, color n successor of n. OK. So now, let's comment out everything below the tree data type. OK. And now let's put in, well, node is really saying not just a color, but a color nm. So we indexed the type of colors by how they relate the heights of the trees. So now what we've got is a data type of trees that carries the same invariant information that the proof objects that we were working with before have. OK? OK. So now let's go through and give specs to each of these functions and then implement them and see how they need to change. So for balance, we can write, so what's the type of balance? Balance is going to be like the type of node. So give me any n and m, which are nat, and a tree of n, and a color nm, and a tree of n. And then you'll get back a tree of m. Right? So that's just like the spec for balance that we had before turns into the type of balance. OK, so now let's revise balance. So let's do it this way. Let's just uncomment what's there, and then we'll see where we get type errors, and then we'll fix them. OK? So load. OK, done. The same code for balance that we wrote in the first place type checks with this new type, because we just carry around the heights implicitly. And just like we've been talking about all lecture, the proof for balance morally has the same structure as the code for balance. OK? Now let's do ins. So what's the spec for ins? It's that for any tree of black height n, what you get back is a tree of black height n. OK, so let's uncomment, and then we'll fix the type errors. OK, fixed. The proof for ins had exactly the same structure as the code for ins. So if you just carry these numbers around in the background, the same code works. OK, let's do black and root. So now give me a tree of black height n. And I'll give you back a tree of, well, we still need the existential quantifier here. We still need the sigma. So sigma lambda m goes to tree of m. The lambda didn't quite work out. Yeah. OK. OK. And then if we uncomment, here we actually do need to make a change. And so empty is not a sigma. So we can just put underscore comma empty. And then on the next line, underscore comma node blah, 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 blah. Right? And that's just like the proof we had before, where we just let Agda figure out the index there. Good? OK. And then let's change the spec for insert. OK. And insert is going to say, give me any n in a tree of height n. And I'll give you back a tree of height. Well, actually, this one gets the sigma as well, right? Because it calls black and root. Black and root produces a sigma. Therefore, this produces a sigma, right? OK. And type check. And we're done. OK. So there is an intrinsic verification of this code. And because the proof had exactly the same structure as the code, we barely needed to change the code at all. We just sort of let this information flow around in the background, and we're good. Yeah?
Why not say that the type of black and root is the, if the tree you get is empty, then it's a tree of the same size, and otherwise it's a tree of, the black height is one more.
Because if the node is black, then it's not one more, it's the same. If the input node is black, then the black height's the same. So you could say that it's either one more or it's the same. Or you could say, depending on the color of the root, it's one more or the same. But like the invariant that you need to show, like the invariant we're interested in for red-black trees is just that the tree has a black height without caring what it is. So that's why I just wanted to introduce sigmas yesterday, and this was a convenient place to do it. But yeah, you could prove something more specific. OK, so now we've seen an intrinsic and extrinsic version of this code. And now I hope you know what I mean by intrinsic verification, which is that instead of writing the code and then doing the proof about it, you index the data structures, that the data structures contain invariant information, and then the proof is the code. There's just one artifact there. OK? So that's pretty cool. But what I want to talk about a little is sort of pros and cons of intrinsic or extrinsic verification. So one thing we can evaluate them on is finding bugs. So if we go up to balance, and let's just say that in the first case of balance, we made the node, I don't know, black at the root instead of red. OK. So then when we load the file, we'll get a type error that says that successor of n is not n. That is, the black height of this doesn't work out. OK? So the nice thing here is that when you're doing intrinsic verification, Agda helps you find bugs by type checking that when you do extrinsic verification, you would only find in the proof. OK? So when we went to do the proof, if we'd made this bug, we, of course, would have found the bug because we wouldn't have been able to do the proof. But when you're doing intrinsic verification, it turns the bugs into type checking. OK? On the other hand, this isn't always a win, because sometimes you kind of just want to write your code and not have to fight to get all of the proof through the type checker. Right? So this isn't like clearly a win or clearly a loss. It's a choice. OK? Another thing we can look at is ease of writing the code. So this one was definitely shorter. Right? So when we did the intrinsic verification, we literally just wrote the code we were going to write anyways, and it type checked. OK? Of course, I picked this example to have this property. If you look at the proof of well read, OK? So if you look at the, so there's this other invariant for red-black trees that the no red node has a red child. And let's see, I think Ian can get it on the screen for a second. If you look at the proof for well read, it's in red-black tree, and then let's do intrinsic well-read. OK. So I'm not going to go through it in detail, but here is a data type of well-read trees. Here is the definition of the root having a color. And then if you kind of scroll through the code for a while, balance kind of gets a little bit more complicated. So the first two cases, hold on balance. So the first two cases are exactly the same rotations. The next two are sort of the catch-all expanded out. So remember, balance had this catch-all case where it just made a node. And this is just that expanded out because it turns out that the proof for the catch-all is different in different cases that we're getting caught by that catch-all. So when you superimpose the proof in the code changes. OK? And then if you keep scrolling a little more, OK, down to ins. So if you get ins on the screen, so the code for ins turns into these three lemmas here. OK? And the reason for this is I don't think this is exactly necessarily a loss. So that really small code for ins turned into a lot more code. But the reason for that is that the reasoning that it takes to see why ins is working really depends on whether you're inserting into a red tree or whether you're inserting to a black tree. It's totally different. There's this kind of neat back and forth. It's kind of a state machine where you're doing one thing for red and then you're doing another thing for black, and you switch back and forth between them, and it always works out that you kind of fix things up at the end of the day. So there's this subtle thing going on in the reasoning that's not present in the code. And when you do the intrinsic version of it being well read, the code is really reflecting that reasoning that goes into the proof. So it's kind of up to you. Like, do I want to read the short thing and then read a proof that explains the reasoning that went into it? Or do I want to read one artifact that's sort of more forced by type checking? If you try to write this with these invariants, there's kind of only one thing you can do. Whereas if you try to do the other one, well, you have to like remember where to call balance and things like that. Okay? So there's this trade-off between, it's more verbose, but on the other hand, it bakes in more of the reasoning, and that can be nice for thinking about this code. Okay? All right, so if we switch back to the other file. So for extrinsic, let's see. So for ease of writing, I don't know quite how to summarize that discussion, but sometimes shorter, right? So sometimes it's easier to just write the code, and then if you have the algorithm in mind, the other thing is that if you've already written down the code, doing the proof is often just a matter of like banging on refine and sort of following your nose, and you can kind of see how to do the proof more easily. When you're doing the intrinsic encoding where the two are superimposed, you really have to think more because you don't have the code guiding you. So again, trade-offs. These are really two things that you kind of need to learn how to do both and when to trade them off. OK, how about ease of reading? I guess we already talked about some of that, but on the one hand, when it's intrinsic, the code is telling you more of why it's right. On the other hand, sometimes it's harder to parse that simultaneously with parsing the code itself. So it's another one of these trade-offs where, if you want to make a readable code, how much of the invariance do you bake in, and how much do you say, OK, number one, you can understand this piece of code, how it actually works operationally, and then over here, you can read a proof about why it works. OK, efficiency. So sometimes you get exactly the same code out, right? Like here we got exactly the same code out, except we're actually passing around these natural numbers, right? We're constructing and passing around these heights. And there are techniques for avoiding this overhead. Like there are compiler optimizations that would erase this. There's one called forcing. You can look at some of Edwin Brady's work that says that, or when's the Idris tutorial?
I was going to do it Wednesday.
Yeah, OK. So there's going to be an Idris tutorial. And
But
that
we're
kind
going to talk about that.
OK. Well, Idris is the system that does these kind of optimizations. Anyway, so there's optimizations that remove this sort of stuff. But you do have to worry about the fact that the data that you're maintaining to look at these invariants really is there at runtime, right? Because we're case analyzing any data. So that's something to keep in mind. If you do an extrinsic thing, then the data, the extra data, the heights, is only in the proofs, and you never actually run the proofs, so that doesn't matter. So when you superimpose them, you have to worry about this issue. And that's kind of an open area of research, is how to make this code as memory efficient as it would have been if you hadn't been doing this stuff. Can we erase stuff? Of course, there's a lot of benefits to doing an intrinsic thing as well in terms of verification and in terms of efficiency. So for example, you wrote the intrinsic nth function, so what was it called, like nth prime in lab, right? Where you knew that the index was in bounds, right? And if you're doing an index if you're doing nth with an index that's in bounds, then you don't need to do a bounds check. So there are optimizations that are possible when you're doing intrinsically verified code that are not possible when you're doing extrinsically verified code if you want to be safe. So it's really a nice trade-off. So this, I think, is really a big open research issue in terms of how do we get the benefits of intrinsic verification while still making things efficient. What kind of stuff can we do there? And OK, one more thing to talk about, which is multiple properties. So here, if you do the extrinsic proof, then you can write the code. You can do one proof about the black height. You can do another proof about well-read, and the two proofs are totally separate artifacts, right? You could task two people with doing the proof about the black height, the proof about well-readness, and they're just independent. When it's intrinsic, it's all one piece of code, okay? So there's not that much you can do there if you want to do them both intrinsically. So in the support code, I think we've got a version of a intrinsic version that's both well-read and has a black height, okay? And then in the lab, we'll have you look at proving that it's sorted as well. So it kind of gets complicated when these properties all get superimposed on each other. So it's sort of up to you to decide how much goes intrinsically and how much goes extrinsically. But the main thing to realize here is that it's not an either or, okay? You can take an intrinsically verified black height and do an extrinsic proof of well-readness about that, right? So it's not like I commit to one or the other. You can take code that bakes in some invariance and prove other invariance about it. And it's just kind of up to you to figure out how you want to balance these things. And there are also techniques for relating different pieces of code. This is sort of another big open area of research in independently typed programming, is how to handle this issue of multiple different refinements of the same piece of code. For the extrinsic, it's totally clear. It's just separate things. For the intrinsic, it's really an issue. OK, so the main thing to take away from this is just that intrinsic verification is really nice when it works, right? Sometimes you get something that's just the piece of code. You put in a little bit of information. Agda checks all the invariants behind the scenes. When you make a bug, you get a type error. It's really nice. But sometimes you really want to do the extrinsic verification. So don't think of this as like, I'm an intrinsic verification person or I'm an extrinsic verification person. They're just two different tools.